Okay, good morning S1. In this video we're going to look at friction and air resistance. Firstly, you can pause the video and have a look at these examples. Which of these need friction to work? Okay, you should also try and put your answers in alphabetical order. So the answer is football boots need friction to work. So football boots rely on you putting your foot forward, pushing your foot down to the ground, and then being able to rely on that boot not moving when you pull against it to bring you forward. Ice skating, so it relies on a certain amount of friction. You need to not fall out of your ice skating boots, but it relies on the boots themselves not having a lot of friction with the ice. Lighting a match, that relies on friction. You're relying on the force that is produced when you press this match against the paper and pull across, being enough to generate energy to light that match. Pencil sharpener, again, you put it in, the pencil pushes against a sharp object, and when you turn the pencil, the friction and the force is enough to keep the shavings pushed against that sharp element and shave the pencil. Rock climbing, you put your fingers into cracks on hexes and cams and things, and then you pull up. You rely on your fingers staying where they are, and I mean, really, with rock climbing, you should be pushing with your legs rather than your arms. But anyway, you need to push off the places you have friction and move your body up. Rubbing sticks together, again, like lighting a match, it relies on friction. Sanding down wood, you've got a rough element, we'll come on to that later, that is pushed against the wood, and as it goes along, it tries to smooth out that wood. It relies on friction. Sledging, you don't want a lot of friction really, it's like ice skating. You want friction with the board. If you don't have friction with the board, you will fall off. You want the board not to have a lot of friction with the snow, except for when you want to stop. And tubing, again, it's a similar thing. You want friction with your swimming costume, obviously, and with the ring. You don't want the ring to have a lot of friction with the water. So, learning to describe friction, we're going to look at what's meant by friction, name and give examples of the effects of friction, and describe the ways to reduce friction between surfaces. So what is friction? Write down what you think it is, and I will answer on the next slide. Okay, so the answer to this question. Every time I ask a question, try and pause the video so you can answer yourself. Friction is the force that opposes motion when two objects rub together. So this is the definition you need to write down, and it answers one of the questions from our assignment. So friction, we'll go through this, is the force, so something that is pushing an object in one direction, that opposes motion. So again, so we're moving in one direction and there is a force that pushes in the opposite direction. We know from my last video with you that really if you want to keep moving forward, you need to unbalance the force that's pushing in the opposite direction. So you need to overcome friction if you want to move when two objects rub together. If we were in school, we would be doing an experiment with balances. You would look at the fact that the more force is pushed down, the more friction seems to be generated, and the more force you need to put in to move the Newton meter. So which of these things do you think removes friction? Being rough, being smooth, being dry, being icy, being soapy, being wet. What other surfaces can you think of that reduce friction? Name 3 situations where friction is actually good. Okay, so the answers to these questions. Being smooth, icy, soapy, wet. So if you think about a big kind of bumpy, craggy substance and another big bumpy, craggy substance, if you put the craggy ends together and try and push straight down, the bumpy bits will kind of join together and they'll kind of bump and they'll grind and they'll get in each other's way. That's kind of what we're talking about with friction, but at a very small level. So if two objects are smooth, they will have fewer of these bumpy bits to rub against each other. If there's ice, what that basically does is it puts water in the bumpy bits and then it freezes it. So it's the same, more or less, as making an object smooth. The ice itself is smooth, so it fills the gaps so the bumpy bits don't touch. Being soapy allows things to slide over each other. So again, the water moves between the bumpy bits and allows the objects to glide over each other, and again with being wet. Other substances you can think of that reduce friction, so oily things has the same effects. It allows something to go in between the two rubbing objects and take some of that force. And anything that's smooth or wet. Icy conditions when you're driving or walking are obviously very dangerous because it reduces the friction between your shoes and the floor. When you're trying to run a bike or a car, you don't want a lot of friction. In sports like ice skating, running, sledging. In cooking, you want your food not to stick to the pan or your baking tray. So in a bike, I've said in a bike friction's not very good. Where is it good and where is it not good? So how do we think about that? Think about your bike. Where do you want friction? Where do you not want friction? So you do want friction in the tires. Think about why. In the brakes, why. Handlebars, why. Gears, why. You don't want it in the brakes, where and why. You don't want it in the gears, where and why. And you don't want it in the tires, where and why. So you want it in the tires so they can go round corners and not fall off. So when you go around a corner, you don't want your bike to just power slide and glide away. So you want to turn, so you need to make friction between the tires and the ground so you can change direction. You want it in the brakes so that when you clamp onto the wheel, there's friction between the brake pads and the wheel. And the handlebars so that you can steer the bike. You don't want to try and turn the bike handlebars and your hand just slides off it. In the gears so that you go downhill and don't need to get off when you go uphill, so that's to do with friction as well. In the brakes, it slows you down when you want to go fast. So if the brakes are on the wheel, that would be bad. So sometimes brakes get out of alignment and they rub, or wheels go out of alignment and they hit off parts of the frame. In the gears, so if there's too much friction, if you end up in too high a gear, it's bad. In the tires, so that you sometimes want quite smooth road tires rather than big, craggy mountain biking tires. So sometimes you like friction, sometimes you don't. I think it's very interesting. When you, so my bike is old and rusty. At some point in the summer, I'm going to try and fix it up. So there's areas I will put a lubricant, WD-40. I'll put a lubricant around here on the chain itself because I want, the chain is got holes in it and this cam thing has spikes. So that'll be fine. They'll dig in. What I don't want is lots of muck and grease and stuff in here. I want that chain to go around really, really, really easily, and I don't want it rubbing and having friction. What I do not want is, I don't want this spiky thing to move. What I don't want to happen is when I put force from the pedal and make that chain go round, I don't want this metal spiky thing to spin round and round and round and round with that force. It needs to stay where it is in relation to the bike. If that spins round, your bike doesn't actually go anywhere because the force you're applying is just being used to spin this thing. What you need is that to stay exactly where it is, the chain to go round, and that needs, this spiky thing needs to be attached to the tire. You don't want the spiky thing spinning around with respect to the tire. It needs to be right against the tire with lots and lots of friction so that when you turn it, the wheel moves. So there's some areas you want friction. You want friction here where the wheel attaches the frame, because again, if there's no friction there, the bike wheel will be just spinning. You want friction basically anywhere something is attaching the wheel, the bike, the seat, the handlebars to the bike. You want friction, so don't put WD-40 there. And anywhere that's supposed to be twirling round and round and round, you want WD-40. So we're going to look at useful and non-useful friction. So this guy's trying to pull a truck. We want the truck wheels not to have a lot of friction, but we want his feet on the ground to have good friction. You want your shoes, the soles of your shoes to have lots of friction. But you don't really, if you're running down a hill and you put your hand on a wall or something, you don't want your hand on the wall to have friction. If you want to make your hands hot, you can rub them together. That generates heat through friction. That's good. If the road is really, really icy, you want to put salt on it and increase friction. And if you're running around, you don't really want to slip on the floor. So some elements you do want friction from the ground, and some elements you don't. So have we go at some of these questions? These are just things you can think about. So pause the video and have a look. So we're now going to look at air resistance. So we've talked a little bit about this in my last section with unbalanced forces. This gentleman here, he is applying force down the way. There is air hitting him, which is providing air resistance, but really his force under gravity pushing down is massively exceeding the force going up. So he's going to accelerate through unbalanced forces until he reaches a constant speed, which is called his terminal velocity. So he's going to be going quite fast. This gentleman here, he is using maybe the same, it could be the same person in different situations. He's using the same force, the same mass and weight to push down towards the ground, but he has this big canopy parachute above him. And what's happening is the force that is pushing down has stayed the same, but the force that's pushing up has been increased. We've got a much larger surface area to catch the air and increase this force that's pushing him back up. So this gentleman's terminal velocity will be a lot lower. He will go slower heading towards the ground than this gentleman here. We can think about this in cars a little bit. You drive forwards quite fast, maybe up to 70 miles an hour in a car. So you're pushing forwards at 70 miles an hour and you're hitting off air particles. And the air particle hits your car and it goes, oh, God, there's a car in my way. And it gets squashing. Air particle behind it hits it. And it has to, all of them have to go up and over your car. They can't go through it unless you have no windscreen. So all the air particles that hit here, they all get squished together and have to go up over the front of the car. That provides quite a lot of force that pushes down, so that stops your car flying, basically. So the force that goes under the car just whooshes right underneath it. The force that hits the front of the bonnet, and then all of the air that hits everything up to the front until you get above the car, it all gets pushed together and has to flow in one stream over the car. So that's providing quite a lot of force. That's trying to prevent your car moving forwards. It's trying to balance out the force. What we can do is we can try and make it so air isn't getting stopped. It's not providing a force when it hits the front of the car. So over here, what you can actually see they've drawn a line. Sometimes they do this in an air tunnel with powder. When the air hits the front of the car, it's pushed up, and you'll see it's not going vertically, and it's not all getting gobbled together at the front. It's all of this air here, is going right over the car. It's nice and low. And there's very little air that actually hits a solid flat surface on the front. Anywhere it has to hit a surface, so the front of the engine, the windscreen, is really, really angled backwards. So all the air whooshes over really, really quick. And you see there's not a lot of a gap underneath. So this car's quite low. It doesn't have a lot of air running underneath. So this air is not going to come under and then push the car up and flip it. Something like a truck, obviously they are quite big. They do have quite a flat front face, so they have quite a lot of air resistance. But even then, if you look at a big megabus or a truck or something, you'll see they have this little cool hair quiff at the front. Now that is designed to, when the air hits the front and it gets pushed up, not have it then hit the back part here of the carrying section. So when it goes up, it's got this nice streamlined, is the word we use, shape, which pushes the air up and over. So basically all cars, if you look at them, if you look outside of your own car, it's streamlined as much as possible. Even the wing mirrors, quite often in modern cars, have this kind of flattened, rounded effect. We're going to try and do a little experiment, which is referenced in the assignment. So I would like you to get a bit of paper or your jotter and draw this table in. There are 1, 2, 3, 4, 5, 6, 7 stages in making our parachute we're going to go through. So you need to put paper parachute stage, because that's the best title I could think of, and then the 7 options. And then the other bit is time to fall to the ground from a 1 meter height. Obviously you'll kind of be deciding what the height is. As long as you keep it the same for every stage of the parachute, it doesn't matter. So draw this table in, step 1. Step 2 is make the first part of the parachute. So we're going to go through different stages using the same sheet of paper. We're going to change it and try and make it so it takes less time to hit the ground. We're going to try and reduce this air resistance. So the first thing I want you to do is fold all of the sides individually. So start on maybe the long side here. This is actually A3 paper because it was easier to photograph. Fold that in 1 centimeter and then fold the side in 1 centimetre, then the bottom in 1 centimetre, and that. What you're then going to do is hold it so this side, the inside, with everything folded in towards it, is facing down towards the ground. Find a phone or a timer or someone to help you. This is a good thing to do as a family or with a wee sibling. Get them to time it or get them to drop it as long as it's safe. Find somewhere to drop it. You can do it over the banister or you can just hold it in your room and drop it. How long does it take between you dropping it from a set height and it hitting the ground? So drop that first parachute, and then in your table here, I want you to write down how many seconds it took to hit the ground. So you drop the first parachute and you put that in the table. What I then want you to do is, with that parachute, fold it in half. So you're using A4 paper, that will fold it in half, so it is about A5 side. Then unfold it slightly, so it's in this cool tent shape. What I then want you to do is, holding it from the top, so this part of the point here, facing down, drop it again from the same height with the same person timing it, same timer, etc., and then put that number in your table. The 7 stages, the third stage, so using the same timer and the same place, I want you to drop, oh, you've done this, you've dropped the second parachute already. This time, what I want you to do is put holes in the paper, so you can see it's had the sides folded in and we dropped it, it's been folded in half, we dropped it, and now I have put, if you think of it as 4 quarters, which you could do, I've put 2 holes in each quarter. The way I've put these is very important. So try and make it so it's roughly in this shape. So on the long edge you've got 2, and on the short edge you've got 2, and they roughly line up. There's a stage later on where we're going to make rips between them, so try and line them up like this. Once you've done that, again, face it down. You can tent it slightly, it's up to you if you want, and drop it and time it. You're then going to, this is why it was important for the placement of the holes, you're then going to make nice neat tears. I did this by hand, so it's not very neat. This is kind of what you're aiming for rather than this. Nice neat tears, like this. And then again, without doing much else to it, you can put it in the position it was in before and drop it, and this will go in your table. So by now we should have done unfolded, folded, 8 holes, and the 4 tears. So this is the 4 tears section. So we've dropped it again. I think there's only 12 of these, so we're at 10. Carefully tear along top and bottom. So what I've done here is, from the previous one, I've torn here, and I've torn there. So it's made 2 flaps. I've not done a lot with the flap. We've not got to the point where we've folded it in. Just make the flaps there. Maybe bend them back a little bit, and then try and drop it again. So this is the 2 flaps stage of your table. And then this is the second last stage, we're going to fold the flaps in, so fold over and then fold the other one over, so you've got these 2 holes. Don't rip the flaps off. At the moment we're trying to keep the paper the same mass, so we're not wanting to take bits off the paper. That actually doesn't matter. Objects don't really fall based on their mass, but we'll look about that actually in a video later. So we've got the 2 holes, again face it down the way and drop it, and then the final stage is, I've not ripped it off completely. You'll see what I've done is I've just ripped at the top, and then I've folded it back to where my thumb is. So you can see the paper is still there, and because I'm using quite strong drawing card, it kind of does stay out of the way. What you're then going to do again is turn it upside down and drop it, and time to see how long it takes to get to the floor. You should now have filled in your table. What did you find out? You might notice that at certain stages it didn't really make much of a difference to the time. You might find at certain stages it made a massive difference. You might find that, hey, nothing really happened, and then suddenly I made those flaps and oh my god, it just dropped to the ground. Or really, it was that stage where you finally got a bit more of a change. Or you might find nothing happened. Really, have a think about it, and I would like in the assignment you to write down, just send me a wee message on the assignment, what did you find out? Because I'm quite interested in this. Okay, so the last interesting thing I want you to do is there's a video by a guy called Brian Cox on the assignment. It's really, really interesting. I said it didn't really matter here, really, about removing that. I said that actually objects would fall at the same speed. Technically, in space, none of this would have made any difference. This, this, and this would all have fallen at exactly the same speed. Now, that sounds a bit weird, but actually it would also fall at the same speed as a bowling ball or a car or a laptop or anything. Now again, you might think that's rubbish. The video will show you its air resistance. What we've looked at, the friction caused by the air particles that is causing it to fall at a different speed if it's a bit of paper or a bowling ball. The video will show you this, and it's very, very cool. Okay, hopefully that made sense. I'll go over it again in the meet. Thank you.